Okay, and let's now switch. And okay, here we go. So today is a very special day. It doesn't happen in the history of mankind that often that you have lecture 21 on May 21st of 2021. Isn't that something? Three 21s all in a row. So you're the only generation that will experience that. All right. Okay. So let's start. Let me first summarize where we are uh, as far as the Duhamel integral and general loading function goes. And we will finish today single degree of freedom systems, and we will introduce multi-degree of freedom system, which I'm really happy because we have a full 2 weeks to do that. I usually don't get to do it for more than like a 2 or 3 lectures. So we'll cover more topics. But anyway, so let's go back to Duhamel integral. So we had, if we had a general forcing function, the solution came down to these two formulations. For the case of undamped loading, you evaluate u using this integral, right? Sine omega n t minus tau d tau. And if the system was damped, the response was the solution to this integral, f tau e to the minus zeta omega n t minus tau sine omega d t minus tau d tau. Okay. Well, we've seen for a few simple cases how you perform this integration, but what happens if you have something, a forcing function that is quite complicated, is not a simple step loading or a ramp loading or blast loading? How do you solve the problem? In other words, such a complex integral, if you're dealing with a very complex type function, how do you do that? So let's look at these two integrals. Let's first consider the case of undamped. So you have u, I will let me rewrite that, 1 over omega n, 0 to t, f tau, sine omega n t minus tau d tau. So the way you solve the problem, of course, depending on, independent of what kind of a function you have, forcing function, first you would replace this sinusoidal function by its trig identity, right? So because you want to um, separate those components that are a function of t from those that are a function of tau, because it's a function of tau that is a variable, and t is treated as a constant in this integration. So you would, for instance, in this case, you would write this as sine omega n t cosine omega n tau minus cosine omega n t sine omega n tau. So simplifying this, you get what? You get 1 over m omega n times sine omega n t, because t is a constant, right? Variable of integration is this dummy variable tau. So it comes out of the integral. So at this time, sine the integral of f tau cosine omega n tau d tau minus cosine omega n t integral from 0 to t of f tau sine omega n tau d tau. Okay, so the problem then comes simply down to what? Evaluating these two integrals, right? That when you perform, if you can perform those integrations, you end up with two time function, basically two time functions, A and B. So if you can solve, let's assume you can solve those, the solution would be what? 1 over m omega n times A sine omega n t plus or minus, doesn't matter, B cosine omega n t, right? And of course, both of these are functions of time. But again, you look at this closely now. This looks familiar, doesn't it? You can rewrite this, right, in this form. A squared plus B squared, right, times A over this sine omega nt minus B over this cosine omega nt. And by now you know that this will become just a sinusoidal function, sine function, omega n t, say plus or minus theta, where theta is the arc tangent of, let's say, b over a, okay? But the point is that this whole integral, this whole response comes down to something like this. The solution becomes a squared plus b squared, square root of that, over m omega n sine of omega n t plus tau. So this would be the solution. In other words, is a sinusoidal function with an amplitude, which of course would be variable, varying with time. So the whole thing comes down to evaluating these two integrals. You can do that. You can evaluate these two integrals, A and B, okay, this is f tau cosine omega n tau d tau and f tau sine omega n tau d tau using some numerical integration schemes. You have seen some numerical integration in calculus. For instance, you remember Simpson's rule, that you use basically a finite difference approach to solve for integrate a function. If you break that down to very small increments, and so you basically say that, okay, the integral of this function would be the sum of the areas of all these rectangles. The way you do that, there are definite schemes of doing it. One of which you covered in calculus was, for instance, Simpson's rule. There are many other different and more advanced time integrations, especially time integrations, that you can find various, for instance, toolboxes in MATLAB to do that. But it is possible to numerically evaluate these. Therefore, it is possible to evaluate numerical Duhamel integral for any kind of general loading function. Even for the case of damped system, where of course, the integral is more complicated. You have something like this. You have f of tau times e to the minus zeta omega n t minus tau sine omega d t minus tau d tau. Obviously, this part still can be expanded the way you did it with the case of undamped, right? Okay, so you have this cosine of omega d t sine omega d tau. So this, you expand this, and this function is what? Is e to the power of zeta omega n tau over e to the zeta omega n t. So this is constant, this is constant, this is constant. And when you're dealing with this integral, t is treated as a constant, so they can come out of the integral. So u, in this case, would become something like this: e to the minus zeta omega n t divided by m omega d. Then you have these integrations to perform. You have f tau, right? E to the zeta omega n tau times, if you do that, times sine omega um, dt cosine omega d tau minus, of course, the integral, right? Minus integral f tau e to the zeta omega n tau cosine omega d t sine omega d tau, right? So this is a constant, this is a constant, so it comes out of the integral. So the problem is simply reduced to something like this: e to the minus zeta omega t m omega d times, okay, something like this. That would be um, a function of t again times sine omega d t minus another function of time times cosine omega d t. That's what it comes down to, where c of t in this case is this integral from 0 to t f tau e to the zeta omega n tau cosine omega d tau d tau, and d is this integral f tau e to the zeta omega n tau sine omega d tau d tau. So if you can perform these integrations numerically, as you did in the previous case, you just substitute them here and you're all set. And again, if you look at this, again, that can be written as c squared plus d squared times sine of omega d t minus or plus something like alpha. So it is a sinusoidal function, but the the overall solution would be something like this: omega dt e to the minus zeta omega n t sine, and of course, c squared plus d squared, sine of omega d t, let's say plus minus alpha. So now you have a sinusoidal function with an amplitude that is exponentially decaying, okay? But nevertheless, the whole problem is reduced down to finding A, B for the case of undamped, or C and D for the case of a damped system numerically. And there are many schemes, as I said, that you can use to do that. Um, you know, of course, I'm not going to get into that. We're not going to discuss it in this course. I'm just introducing you the concept. But if you want, you can go and look it up. Use if you come across any function like that, look it up. Use some MATLAB toolbox and numerically integrate. Uh, those functions. You can also use, if you have a general loading function, you don't have to use numerical, you don't have to use Duhamel integral in order to solve the problem numerically. If you have something like this, you can numerically integrate this differential equation by dividing the time, the forcing function in the time domain into small increments of time, and use a variety of integration schemes like Newmark uh, beta or Rankara, Ranjikara, two Indian mathematicians who introduced a very powerful approach for numerical integration, widely used. That algorithm is widely used in some complicated even cases. But anyway, so there are many different schemes that you can use to numerically even solve this differential equation. I just wanted to give you a brief exposure to the general approach for solving both Duhamel integral, or in general solving the equation of motion when the forcing function is very complicated. So if you come across that, at least you have some background for that. We're not going to discuss that in this course, and it's not really within the uh, scope of the course to go get into numerical integration. Any questions? I also, before we go any further and start the coverage of multi-degree of freedom systems, I wanted to also um, introduce to you another concept. We're not going to, again, discuss it in detail, but it is important for you to know, especially when you maybe working, if you get to work in a company that you're dealing with the manufacturing of equipment, especially sensitive equipment, um, and you come across that terminology called uh, shock uh, spectrum. Okay. In fact, somebody last time asked me a very good question, and that is, well, if you have a sinusoidal loading or harmonic loading, you can easily find the maximum response by having the frequency response function, which you can obtain, right? So the maximum response in any dynamic system subjected to harmonic loading, you know by now, can be found from this relationship where h was the frequency response function. But that frequency response function is only valid or uh, is used in the case of harmonic loading, or in the case of periodic loading, because the periodic loads can be also converted to a series sum of harmonic loads. But what happens if you don't have that? If you have a, say, a shock load, a blast loading like this, how do you find the maximum response? Or how you could find something analogous to this relationship, okay? In these cases, when you have general loading like this, the maximum displacement depends, as you saw, for instance, we solved this problem, it depends on not only the magnitude of the load, but also on the time duration. So it is important if we can come up with an approach that, depending on what this time duration would be, you can find the maximum response as a function of that. In practice, in fact, we do this. Every system has its natural frequency. So is it possible that we find a function that is a function of this non-dimensional variable, time duration over the natural period of the system, and come up with a relationship like this? That is called response spectrum, okay? If you go back to your notes last um, session, we solved this problem with a undamped system subjected to a blast loading like this. And we came up with the maximum displacement, which was something like this, which was F naught over T omega naught times 2 times 0.227 sine omega nt minus 0.1248 cosine omega nt. In other words, for that problem, you could see that U max over F0 over K, well, actually this was K, was a function like this, T omega naught times this, okay? And in, and in fact, this was T naught, okay? If you plot this function for that problem, you see that you get a curve like that looks like this. If you plot that function as a function of T naught over natural PSC, you had omega n, right? So you convert omega n to 2 pi over t. So you have t, which is the natural period, and then you reformulate this and express that equation in terms of T naught over T, and you plot basically this U max over F0 over K, you get a function like this. What is the beauty of this? If you have a loading like this, okay, you want to know what is the maximum displacement that this system experiences. Let's say T naught is, let's say, is 0.1. So you find T naught over the natural period, you get some value here, you go here, and you find the maximum displacement of that system. So for a wide range of typical loadings like this. These curves have been plotted for a single degree of freedom system. This is for a single degree of freedom system. Okay. So if you're given a shock loading like this, you have this shock spectrum or response spectrum, and you go to that and you can find the maximum displacement that your system would experience depending on the time duration and the natural frequency of your system. And therefore, from there, you can find the maximum stress and maximum strain and so on. So I just threw this at you, the concept of shock spectrum. I'm not going to go over that in details. If you want, I have several examples in these notes, which I have on YouTube and in Zoom lectures. Uh, if I'm not mistaken, those are lecture 22. I'm sorry, those are in my Zoom lecture notes. Lecture notes. I don't have them on YouTube, but I'll be happy to send those who are visiting my YouTube lectures and they want those notes and those examples. I will do that. But there are two, I have done 3 or 4 problems, how you derive the shock spectrum and how you use that for those of you who might be interested to learn more about this topic. But I don't expect that from you, and I'm not going to cover that in final exam. Something that at least you remember this terminology someday if you're dealing with that. You're designing a rack system for all these servers for Amazon, and they tell you, okay, this warehouse is built, this region may be subjected to some shock loading, let's say earthquake loading or blast loading, and I want you to make sure that these racks are safe. So as a mechanical engineer, you put in charge to, given the shock spectrum for that region, find out what is the maximum stress that those racks will be subjected to, and you design it, you're proud of it, and you would think of me that I had a professor 20 years ago who's dead by now, but he at least introduced that concept to us. Any question? If not, let's pause and see where we are. Up until this point, we basically covered a simple representation of vibratory system by modeling them by a single degree of freedom system. We discussed the free vibration of these systems when they are undamped or damped. We discussed forced vibration of these systems for the case of undamped and damped. Of course, for the case of forced vibration, we discussed harmonic loads, periodic loads, and general loading. Through this, we saw how we can find the maximum response of a system. We introduced concepts such as damping ratio, frequency response function, natural frequencies, and we saw that by the simple modeling of mechanical or structural system as a single degree of freedom system, you can do a lot. But the basic premise for modeling a system as a single degree of freedom system was that you could think of a system that is vibrating. Its displacement shape is analogous to a static displacement shape and very small deformation. So you assume that, okay, the entire mass that is moving this system is lumped at a single point, and it is the motion of that mass that is representing the motion of this vibratory system. In real world, that's not the case. You cannot think of the entire mass being lumped at a single point. You have a system that, even a simple cantilever beam, that is mass is distributed. And if you don't want to deal with that distributed mass, you would say that, okay, at least I can think of this beam as a series of masses lumped throughout the structure. Regardless of what basically assumption you make, you're dealing with a system that is no longer, you know, is a single degree of freedom system. Okay. In fact, you've seen that in lab experiments that you have done, that if you consider a cantilever beam, depending on the intensity of the input frequency, this beam may displace like this, right? Or may displace like this, or may displace like this, okay? So if the input frequency or the intensity of the load is large, system will no longer behave in such a way that you can think of it that the displacement is similar to static displacement or a very small displacement, so the system can be represented by 1 degree of freedom. You have two choices in dealing with system in the real world, that they're not really single degree of freedom system. Either you model them as a series of masses connected to each other, or deal with the system as it is. This formulation brings us to introducing multi-degree of freedom system, which is a representation of a system by discretizing or breaking down that system into a set of lumped masses, or you can deal with the system as is, which is a continuous system. Each of these are basically two different coverage of mechanical vibrations. This is treating mechanical vibration system as continuous system. You will be dealing with partial differential equations that you cannot even in general solve them. So at the end, you have to come to numerical integration. But this in itself is a course by itself, continuous vibrations. And or dealing with systems as multi-degree of freedom, discretized, lumped masses. And that's what we are going to introduce. So we are now going to discuss the topic of multi-degree of freedom systems. And in order to do that, we always start with simply a 2 degree of freedom system first. In other words, let's first start with a simple case that, let's say, if you have a beam, you have broken down this beam's mass into two masses, and so each of them representing a degree of freedom, and you want to formulate the problem. You may say that this is too simplistic, but this approach is really an introduction to multi-degree of freedom system. By formulating first the equations of motion using only 2 degree of freedom system, we will see that we can do hand calculation for very important concepts, such as finding the natural frequencies and mode shapes of the system. And so you get a better, good, in-depth appreciations of what these dynamic characteristics are. Also, by doing that 2 degree of freedom formulation, once you set that formulation in terms of a matrix, that will introduce the fundamental concepts and how you would solve dynamic response. Okay. So for that reason, we will start with 2 degrees of freedom system. Okay. And you will see that through that, we can introduce some new dynamic characteristics that we haven't discussed, such as mode shapes, uh, normal modes, orthogonality, and all these concepts that are the foundation for dealing with multi-degree of freedom systems. So let's get going. So this is what we are going to do. We start with a 2 degree of freedom system. Okay? That is, you have two masses, M1 and M2, that they're connected. They're part of a system. And we know that connection is nothing but a stiffness and a damping element. So this is the model of a 2 degree of freedom system, which can be subjected, each mass, to a separate forcing function. The ultimate goal is what? We want to find the displacement that each of these masses experience. Okay? So the mass to experience, okay, going through here, so they're displaced. Make it even more general, we can even consider an input displacement function to the base that this system is connected to. Okay? So if you remember from single degree of freedom systems, the objective was deriving the equation of motion first. In order to do that, we introduced two broad approaches. One, we used second law of mechanics, or Newton's law, right? Setting a free body diagram and deriving the equation of motion, or energy methods. We will introduce both of them for setting up the equation of motion for a 2 degree of freedom system. So first, let's start with this one, second law of mechanics, meaning that you need to set up free body diagrams of these two masses and simply write equilibrium equations. So mass 1, mass 2, mass 1 is subjected to this external load. This one is subjected to this external load. Internally, if this moves that way, you have the force of this spring and this damper that's resisting its motion. Also, a force exerted by this spring and this damper, that of course, there are internal forces between these two. So they act on both masses, equal forces in magnitude opposite in direction. And then you have the lumbar force. If the system, these are moving in that direction, you have M1 times Z1 dot and M2 Z2 dot, where Z is the absolute displacement of these masses, Z2 and Z1. That is, Z is Y plus U. Okay. So this is the free body diagram. So let's write the equilibrium equation for each mass. Simply add these up, these forces. You get M1 Z1 double dot plus FC1 plus FK1 minus FC2 minus FK2 is equal to F1 of T. For this one, I can write M2 Z2 double dot plus F C2 plus FK2 is equal to F2. Easy to see that FK1 is what? Is K1, U1, FC1 is C1, U1 dot, F2, FK2 is due to the relative displacement of that mass, which is U2 minus U1, and FC2 is due to relative velocity, which is U2 dot minus U1 dot. So we just substitute these into these equations. And if you do that, you end up with these two equations in terms of U1 and U2. M1 U1 double dot plus C1 plus C2 U1 dot minus C2 U2 dot plus K1 plus K2 times U1 minus K2 U2 is equal to F1 minus M1 Y double dot. And the other one becomes M2 U2 double dot minus C1 U1 dot plus C2 U2 dot minus K2 U1 plus K2 U2 is equal to F2 minus M2 Y double dot. So you end up with these two differential equations, which are the equations of motion or describing the motion of these masses. If you want, instead of you can express these equations in terms of the absolute displacement. And if you do that, your equations would look like this. M1 Z1 double dot plus C1 plus C2 Z1 dot minus C2 Z2 dot plus K1 plus K2 Z1 minus K2 Z2 is equal to F1 plus K1Y plus C1y, or an M2 Z2 double dot minus C2 Z1 dot plus C2 Z2 dot minus K2 Z1 plus K2 Z2 is equal to F2. So this is another alternative form for the equation of motion with respect to absolute displacement. Now let's pause and look at these equations that describe the motion of these two masses.
Professor, real quick, I have a question.
Sure.
Why in the equations of motion is there an inertial term for the other mass? Like the m1y double dot in the first equation, or the m2y double dot in the second equation? Where did that come
M2U, no, this is U double dot.
on the other side of the equation?
Oh, yes, this one.
Yeah. Where did those come from?
Well, if you write, if you just simply write this, right? What do you have here? You have MZ Z1 double dot, right? So Z1 double dot from here is U double dot plus U1 double dot, okay? And same thing for Z2. So if you substitute for Z1 and Z2, okay, you end up with this. I skipped that step, but that's where this comes from.
So is z the absolute position, and then
Correct.
u and y are the relative ones?
Exactly. Z
Okay.
is the absolute, uh, displacement, and U's are relative displacement. Yes. We'll discuss this, of course, in more detail next time. I just wanted to derive these equations, and we just pause and look at these. The difference you see between these now and the case of single degree of freedom system is that the equations of motions are coupled. In other words, each differential equation is in terms of both U and U1 and U2. So how can you solve these differential equations? We will see that next. We will start the process for solving them. We won't see it uh, actually until a few weeks from now when we introduce the concept of modal coordinates. Because the only way you can solve these equations and find U1 and U2 is to transfer these two equations into a different coordinate system. Not U1, your coordinate system now consists of U1 and U2. We need to find a different coordinate system that you would transfer these two into that coordinate system. And there, these equations would become decoupled, and in terms of new variables, new coordinates, that we call them modal coordinates. You solve for the displacement in that coordinate, and then to transfer those back to find U1 and U2. That is the whole objective of studying multi-degree of freedom systems. But before doing that, we need to learn some more basic concepts, such as what is the natural frequencies, what are the mode shapes, and orthogonalities, and so on. So I'm going to stop right here, and we have just started multi-degree of freedom systems, and we're going to continue next time.